Good afternoon. How is everyone doing today?
Good afternoon, Professor. I'm good.
Good afternoon.
Good afternoon.
Hi. All right. So it's been almost half of the semester. We're in week 7. Have you guys ever had a midterm one in your lecture class yet?
Yes.
Yeah, I have.
Had? How did that go?
I went better than expected.
Better?
Yeah.
At least I think. It's not great again, but I think it went well.
Better than you expected? That's good to hear.
Yeah, mine, kind of the same place.
Okay.
Yeah, a little bit better than I expected.
Okay.
Not the best, but at least better than I expected.
No, that's good to hear. Which part strike as surprising to you that you feel like, oh, I didn't know that, it's case like this, I should do better next time. Anything that you might take away from that first midterm?
For me, it was the time. I think, yeah, like an hour sounds like a lot, but in reality, it was like I barely could get one question finished, and like the rest I did a lot of work for them, but like I did not have time.
I see.
So yeah, I think the next one for sure I have to manage my time better.
Right. How many questions if you are given an hour?
Ooh, how many was it? I think was it 5? Was it 5
5
questions?
questions? Okay. That
Something
sounds
like that.
about right, reasonable. When we were doing this in person, obviously the class time will be the exam time. I think if there's one good thing about online exams is that you could give it a little bit more time because you're not really using the lecture time. So yeah, it could be a little bit more flexible, but 5 questions would really depend on the type of questions. Sounds reasonable.
Quick question.
Yeah.
I don't remember if this is on the syllabus or not. We don't have a midterm or final, right?
For the lab, no. Labs, there are 3 or 4 quizzes. I don't remember his exact amount. And then we have a final quiz, sort of, as our final exam that's at the last week. But yeah, but it's not like your lecture course where you have a final exam and then 2 midterms. But they're like little quizzes. I think these are more frequent. Checkups are good because one quiz, the weight of that is much lower if you have more frequent quizzes. And then for us, the labs, the majority of that is still your worksheet. So it's easier to get a better score on the worksheet because you have, unlimited time to prepare and you can always ask your instructor. So, all right, just want to check with you to see how you are all doing. Now, I'm teaching a lecture myself too, so it's okay if you want to have any question about this class in general with the lab or with the lecture portion, no matter what it is, you're welcome to come discuss with me and talk to me. I'm happy to do whatever I could to help you. So this lab, we're doing lab 7. We're looking at uniform circular motion. So we have already learned this in class. For this lab, we're not lag behind. We have learned this in our lecture, that for an object that's in circular motion, you need a centripetal acceleration. Because even though the speed is not changing, you have a constant speed, the velocity of an object is constantly changing. So do you still remember how to draw a velocity vector on the curve? For example, right now, at this point, the velocity is this direction. At this point, how do we draw the velocity vector? So for a circular path or a curve, the velocity vector is always, how do you describe this particular direction? Sort of the line that right cut tangential, very good, Joshua, is right tangential to your curve. So you can see for circular motion, the direction of velocity is changing all the time. That's because you have a centripetal acceleration pulling toward the center at every location. Okay, so we need a centripetal acceleration. And from a previous lecture, the acceleration is related to the velocity and radius of this motion. Velocity squared over r give you the magnitude of your acceleration. Now to get the velocities, you can use the circumference of the circle divided by 1 time. The total time take for 1 revolution goes all the way around. That's the capital T. You can calculate the acceleration. Let's take a quick look at our pre-lab. Just to recall and familiarize ourselves with these different concepts. So here it's telling us, well, okay, the radius is 18 centimeters, which means it's 0.18 meters. And it takes 29 seconds for 50 revolutions. That's another way to tell us the period. And we have to calculate what is the time it takes for 1 revolution. And we need to find the centripetal acceleration of the object. Okay, so we just talked about you can use velocity over r to find this information. Now you have 2 choices. One is in the slides or in the lab manual, it had already converted the velocity with radius and time. So here, if you had say, okay, velocity is 2 pi r divided by total time, then I just need to plug in the radius and the time, and I can find the velocity. Or you can actually find your velocity from the information that's given and then plug in here. Now, you can also, for velocity, you can also using the angular acceleration. You don't always have to use the linear acceleration. You can use omega instead, right? Omega is v over r, or you might say v is omega times r. This one is your linear velocity. If you're talking about the magnitude is your linear speed, this is your angular velocity. What does angular velocity mean? So in linear velocity, we would say, oh, 2 meters per second, meaning that in 1 second, you have traveled 2 meters. So angular velocity means you can say 1 radians per second. You can say, oh, in 1 second, you have traveled an angle of 1 radian, or you might say 30 degrees per second. Okay, in 1 second, you have rotated around 30 degrees. So that's what angular velocity means. Now, when we use angular velocity, we always use radians per second for its unit. Radians, when you multiply radians by something else, it's not a unit, it's actually dimensionless. So when you do omega times r, the unit from radians is just 1 over s. The unit from r is meters. So this gives you meters per second, which is the unit for velocity, okay? All right, so there are several different places you can start with. You can start with this, or you can use this equation, or you can use this equation, okay? The important thing is to know whatever, which quantity is given and what does it mean. So first, let's figure out the period from this information. It tells us in 29 seconds, it completed 50 revolutions. So what is the period of this uniform motion? What is T? How do we calculate T, the time, for 1 complete cycle?
So 29 over 50?
Yeah, it will simply be 29 seconds over 50. Okay, so that's the time. Now you have the choice of simply plugging the time right here and the radius to get the acceleration. Or we can use that time to find our velocity or find our angular velocity and to go from there. Okay, so 29 divided by 50 is 0.58 seconds. That is our period. So I'm gonna also, now let's calculate V. V is 2 pi r over t. If you wish to calculate V, you would use 2 pi times the radius, which is 0.18 meters, divided by 0.5 seconds. So you can calculate your velocity. Or if you wish to calculate your omega, so in one cycle, when you go one revolution, during that 0.58 seconds time, it goes around one complete circumference. But if you want to describe using the angle, you would say, oh, it had gone all the way around 360 degrees, which is 2 pi in radians. So it's 2 pi over time. Okay. So if you are calculating angular velocity, it's simply 2 pi divided by 0.58 seconds. So you can use either of those equations and you can find your acceleration. It's about 20.9 meters per second squared. Okay. So that's the final answer. Are there any questions about how we calculate centripetal acceleration?
Yes. So the 20.9, that's the answer that you got from the velocity. Yeah, from like the velocity equation and the angular equation.
Either one. If you use this one, you plug it in here. If you use this one, you plug in here. Or you can directly use the time and plug in here.
Oh, right.
It's all the same.
Right.
And it should give you the same answer, right? Because
yeah,
we
okay.
calculate. Sorry, go ahead.
No, I was just gonna say I forgot to plug in.
Okay. Yeah, don't worry. Yeah, so the important thing is if you to get your equations right, and plugging in is a little less trivial.
Yeah. Okay, thank you.
Any other questions? Any other questions? Okay, so let's go back to our lab for this week. So our goal is to look at the dynamics of centripetal acceleration, which means we will measure different accelerations, and we will measure different forces to see if the force, this force provides the acceleration, so they should obey Newton's second law, okay? And we will plot the forces versus the accelerations. So this is what we're trying to do. And there's a very neat design. Okay, how do we measure the force? It turns out that if we have this body, so it's like a bullet-shaped heavy object, and there is a top that you can turn. So if you turn it, you can see that, well, it's doing a circular motion in this horizontal plane. So doing a horizontal circular motion like this. Where is the centripetal force coming from? It's coming from the spring. So it's attached to a spring. So you can see that the spring is extended, pulling the object in, giving it a force, and that's the centripetal force, and provide the circular centripetal acceleration you need in order to do the circular motion. But you might wonder, okay, but how do we measure the force from the spring? Well, we can't directly. The spring does not have a meter. You cannot read from the spring what that force is. So we measure that force indirectly by balancing it on the other hand. So you can see that, okay, once you start spinning it, right, it's going to, let's say you have a little mark here. This is your little mark, like a tape. Once you start turning it, the spring is this much stretched. But once you stop turning it, it's going back to where it was. But we can find out, well, if the spring is stretched for this much, how much force is needed to stretch the spring? So we can measure the weight on the other hand, through a pulley indirectly, because the weight of this mass is mg, and the tension will be equal to this weight. So let's say if you hand 5 pounds of mass here, which means there's 5 pounds of force in the tension, which means the tension everywhere in the string is the same. So you have a 5 pounds dragging in this way, then the force from the spring must be 5 pounds. So we cannot measure the force of the spring directly, So instead, we measure the hanging weight as the indirect measure for the force. Okay. So you can see that we will use different, we will change our screw so that every time when your spring is at this mark, it actually gives you a different amount of force. So which require you to balance it with a different amount of weight. So you might have a lot of different weights. You start with 1 pound, 2 pounds, 3 pounds, and 4 pounds, and so on and so on. So, and every time you should measure a different acceleration. Okay, so now we talked about and figure out how to measure the force. And then we need to talk about how to measure the acceleration. Again, well, how do we measure the acceleration? You might recall, well, in our previous lab, we measure velocity using the sensor. Here, we're not going to use the sensor. We're going to use our own stopwatch, okay? So we're going to time it because velocity is really what? Velocity is really the circumference divided by the time. We know exactly what is the circumference because we know, okay, if it's doing a circular motion, we know what the radius is, it's the distance. We know exactly what the distance is, right? We can do 2 pi r. All we need to know is how much time for it to go all the way around. And then we can find our own velocity. Now from that velocity, we can find acceleration, right? So that's also an indirect measure of the velocity. The one thing that we have to take data is using your stopwatch. You can use your phone to measure the time. So you notice that I will show you the video soon. 1 revolution is very fast. So you can't exactly tell when it starts here and when it goes away one way around. It's not also not going to be accurate if you try to measure the time for 1 revolution. So instead, we'll measure 50 revolutions. We count that it passed by the same mark 50 times, and we simply divide the total time that we measured on our watch, divided by 50, we get the period, the time for 1 complete rotation, 1 revolution. So that's more accurate, okay? So that's how we get forces and how we get the acceleration. We get each of these, and then we eventually will plot it. So before we go look at the video, there are a few different things we need to talk about. One thing is, okay, to get the added weight, to get the force, you need to see how much mass you're using. And there is an uncertainty associated with the mass. The uncertainty is decided at the beginning of the video, because to move the body to, let's say, 18 centimeters mark, you might realize that you can add or take away a few different masses, and you still consider that to be 18 centimeters. So that gives you the uncertainty. The max minus min over 2 method give you the uncertainty. And then you will read that at the beginning of the lab, and you write the same uncertainty for all the masses. Okay, there are 4 different trials. And at the beginning of each trial, they will tell you how much mass they're using. And then you're going to time it, count for 50 revolutions, and put in your time for each of these. And you can kind of time your, do your time average and your uncertainty. Okay, so before we do more about the data, let's take a look at the video. Okay, this must be a video. Okay, are you able to see the video, right?
Yeah, we can.
Okay,
Yep.
so here is where they start doing mass uncertainties at the very beginning, and you will use the same mass uncertainties for all of your calculations. Move this up a little. Okay, let me just try to, if only I could move this up a little. Okay, so let me
determine a minimum mass, but we want to ensure that we still complete the object what we consider to be 18 centimeters.
That's your minimum mass. And then eventually they'll show you the maximum mass.
Now we're going to find the maximum. And that's done by slowly adding masses until it is bigger, but still within a range in which we would call it 18 centimeters.
Okay, so use this max minus min that was given, divided by 2, you get the mass uncertainty.
And that's it. In the determined by the they stop in a speed
Okay.
average time. As we cannot see time, this method of simply repeating multiple measurements allows us to determine a
The first trial, the start with the forces, they're changing the different weights, right? The first one, they start with 1100 grams, okay? So they start with 1100 grams, and you can see that they've always put their tape at 18 centimeters mark. But the force is different. All they did not drag the spring longer or shorter, but instead they changed the screw so that the force from the spring is still different. Okay, so that they don't have to move the 18 centimeters mark every time. So I want you to do a timing activity practice together. We all do it together. So once the body swing across the tape, then you can hear a sound. You can also see it. That means that rotation is at 18 centimeters, and you can start, begin on your time watch on your phone, and start counting how many revolutions. So count 50, because for each of these masses, they actually do 200, okay? So you choose 3 different periods within that 200 to be 50 revolutions. And these different periods could overlap as long as you choose 50. But notice sometimes they spin a little bit faster, they might move a little bit further. So it doesn't really hit the 18 centimeters mark, but quickly they adjust so the body moves back where you hear the sound again. So I want to let you know and remind you, even when you cannot hear it, you should still count that as 1 revolution. You still need to remember to count, okay? Otherwise the timing will be off. So once they start, we will do our timing to see how much time it takes for the 50 revolutions for the 1100 grams of mass. Okay.
A plausible max and min. Time your oscillations within any of the 200 rotation periods. Make sure you.
Soon enough, you will hear the sound, and you can decide when you want to begin taking data. Okay. When it starts, you say, okay, now it's at pretty much at 18. I'm going to start count 1, 2, 3, 4, 5 until you count 50, and you can stop the watch.
You start at various sections to capture a better average.
I will stop in 10 seconds. Okay, now I will stop. Okay, I hope you were able to count 50 revolutions. That was longer than when I was taking data, but I just made it go a little bit longer for everyone to have a chance to take the data. Anybody would like to volunteer the time they measured for us?
I got 33 seconds.
33 seconds. Okay, for 50 revolutions.
Yeah.
Okay, okay, all right. Let's see other data. Someone got 33.81. Neil. Giovanni got 24.23. Okay, I will volunteer my data. I get 23.78. So you can take a few different measurements. Now, I do believe 33 just a little bit too long, 10 more seconds. So if you get something that's an outlier, which happens a lot in our experiment, simply disregard the data and you can feel free to take your measurement one more time, okay? I think for the 1100 grams, around 24, 23 seems to be within a reasonable range. Perhaps you took data too early when it haven't started running yet. So if that's the case, you can wait a little longer until it settles down. So when you do this experiment, you'll have to do this measurement yourself 3 times for each of the trial. But to do an average, of course, you know how to do the average. To get the delta, what do you do to get the delta for the T? Uncertainty for the time.
Would it be like the highest number subtracted by the lowest number, then divided by 2?
Yes, so it'll be your highest max T minus your lowest max min over 2. So because it's your data, your delta will all be different, okay? All
I
right,
had a question about this part though.
okay.
So we're supposed to count, like we're supposed to count it, how many times it hits the, like it goes in a circle. We're supposed to count that 50 times.
Yeah, how many times it goes in the circle? The fact they hit the mark, the tape, make a sound that helps, but don't always rely on it because sometimes when it goes all the way around, it didn't always hit that tape. Yeah, so just look and also listen at the same time. So yeah,
Okay, so
go around
we have
50
to,
times.
right. So we
From
start
there-
a timer and then we count 50 times how many times there's a revolution.
Yes, exactly.
Okay, okay.
If you wanted the period, which is 1 time, you count that it go around 50 times. And yeah, so this is for the 1100 added mass. So that's the first trial. To get the total, to get 1 period, obviously you divide that by 50 because this is the time it go away around 50 times. But what about 1 revolution? You divide that average by 50. Let's look at it. Sorry, the data is here. You get your period, right? So if this is like 23 seconds, for example, this will be 23 divided by 50. And the uncertainty, also, what do you do for uncertainty? Uncertainty, the absolute uncertainty is the absolute uncertainty you got previously divided by 50 as well. Now, this is the last error propagation rule that we talked about in the very first lab, the beginning of the semester, okay? So if this uncertainty is it's let's say 1.5 seconds, then this uncertainty for the period will be 1.5 divided by 50 seconds. Okay, that's for the 1100 grams mass. For the added weight, now, how do you turn that into newtons? Sorry, this is 1100, but it will be 1.1 kilograms because our unit is in kilograms. So be careful. Make sure you do that conversion. When you do the forces, you need to do mass times G. So the force will be 1.1 times 9.8. That's your force. And the uncertainty for your force is the same. The same error propagation rule is the absolute uncertainty for the mass times 9.8 is delta F. So by doing that, you're able to put in all of these data in, okay? So you can see that only one thing left is, well, we still haven't had our acceleration yet. How do you get your acceleration? The acceleration is calculated by this formula that we just discussed at the beginning of the lab. The radius is 18 centimeters for all the trials. So which means it's 0.18 meters, and the time you just calculated. Okay, so for every period, you have a different acceleration. And also for every uncertainty for the time, you have a uncertainty for the acceleration. So uncertainty of the acceleration is calculated using this formula. And where does this come from? Well, this is actually coming from, again, our arrow propagation rule at the beginning of the lab, the semester. So if you need to refer back, you can go back and check. It tells me that when you have multiplications and when you have divisions, the relative uncertainties of A, okay, is equal to the relative uncertainties of this variable of the other side, okay? But when you have a power, the relative uncertainties is the power times the relative uncertainty of the variable. So this 2 comes from the power, and the relative uncertainties of A is equal to the 2 times the relative uncertainties of your time. And to get the absolute uncertainty, delta A, you use A times 2 times delta T over T. Okay, so that's this equation. So this comes from the lab 1, units and measurements. So you can refer back and review that later. So with that, you're able to calculate all of these quantities and fill in all these data sheets. And then later on in the video, they will show you 3 other masses. All of them are a little bit reduced. 970 grams would be the next mass they use, and then later and smaller and smaller. So until they go through all the trials, and then you plot the data. So you will have a graph, okay? Your x-axis would be your acceleration from here. Your y would be the forces, which you did from here, and you will plot. Now, any predictions? What kind of a graph will we get? Should we get a straight line or should we get a curve? So if our lab verified Newton's second law, what kind of graph should we be getting?
I want to say linear.
A linear, yes. So if you get a linear graph, what does the slope represent? What is the slope?
Is it the number of revolutions?
So if F is proportional to A, then comparing with our Newton's second law equation, the slope would be n, right?
The mass?
The mass, yes. So it's like, okay, what object is rotating? It's that body. And what the force is acting on what object? It's that body. So when you plot the force over the acceleration, you should get the mass of that body. It's going to be the mass of this body, this right here. Okay, that big thing. So at the end of the lab, they will show you, oh, let's put that on the scale. They'll put it on the scale and you can read directly what the mass is and can compare that mass with the slope that you get to see if you have a verified Newton's second. Okay, so that's a way to compare your data that you measure from your experiment using the theory with the actual mass of the object, which you can measure using the scale. Okay, so that's basically what we're doing in this lab. Any questions? Any questions about the data collection or about the calculus, the calculations, anything?
I have a question about the graph. Do we have to, can we do it in Excel or do we have to hand draw it?
You can totally do it in Excel, and I encourage you to do so. With a hand drawing graph, we did require that for the beginning of this class. For one lab report required that because we want you to practice how to do it by hand. You have to use a graph paper, do it carefully. But once we practice that now, to get accurate results, I want you to use Excel, or if you have another software, you'd rather use it's fine. In Excel, you put in the data for A in one column, you put the data for F in another column, you highlight both columns and use plot. You will do a scatter plot okay, X and Y, and you will add a trend line, okay? So the thing is, it's add a trend line, but not to connect the data. So I've graded lab reports. Sometimes our data looks like this, right? And then you cannot connect them like this. That would be wrong. You will need to find the best fit, which is a straight line running across. So the computer will run the line for you to see which one is considered the best fit. So what is the best fit? Best fit is that you fit as many lines on the dots on the line as much as possible. For the dots that's not on the line, you want them to have the smallest distance, overall distance from the line. So if you have one dot above the line, you want to have one dot below the line, but the computer will do it for you. And in the add trend line option, you can show the equation. And the equation, they should show it on the graph as y is equal to, I don't know, 500x or something. You may get an intercept too, because in our lab, you have a little bit error and you may still have some friction. So it may not be exactly cutting across the origin, but that's okay. What you want is the slope. So take the slope and record it here, and that's your measured mass of the body. Okay. And thank you for that question. It's actually really important knowing how to graph the data and read the correct information from your graph. Any other questions?
Yeah, I have a question. I kind of always get confused. I know that the slope is going to be the mass, but what do we write in the brackets on the slope side, like in that chart right there? You know, where it says slope and it says y-intercept, and the slope, there's brackets, right? There's brackets for each of these.
Yeah. You can put your unit in there just in case if you did everything in SI unit, your slope would be, well, okay. Let's use SI unit. This will be in newtons. This will be in meters per second square. So you don't have to write anything here. Just write the number down. I'm just putting a random number there. It's not 5.
Okay.
Y-intercept, maybe it will give you some kind of Y-intercept, I don't know, 80, whatever your data tells you. And the mass of the body will be, if you have already converted your unit, then the mass of the body would be in kilograms, and you write that exact same number as your slope. Does that make sense?
Yes.
Yeah. So if you hadn't converted, maybe if you had used centimeters per second square for your acceleration, then this would have been newtons over centimeters per second. And then you need to do a conversion later to get a kilograms. Okay, but I recommend you do all the conversion in the beginning. So when you get the slope, you know right away that's a kilograms for the mass. Very good question. Any other questions?
Yeah, I just have one question. If we do the Excel graph, do we still have to draw the other one too? Because I know on the worksheet it said hand-drawn graph. So I didn't know if-
Yeah, just use your Excel to replace the hand draw. Every time when it's a hand draw, you can use Excel to replace it.
Okay, thank you.
All right. There is a question about the quiz. Let's see, when is our next quiz? Is it today? It's not today, right? Is it today?
Yeah, it's
I
today.
think it's today.
Okay. Let me see what labs are included, and I'll let you know. Okay, so for this quiz, the labs included are the force and motion lab, the Atwood machine lab, and the collision of the car lab. So basically the 3 labs before today. So it will be lab, let me count it backwards. Today's lab 7, that's not gonna be on the quiz. So you'll be lab 6, lab 5, and lab 4. So it's the first 3 labs we already did on our first quiz. So lab 4, 5, and 6. Any other questions? Any other questions? Okay, All right. If there's no further questions, I will see you guys next week. Again, if you have any questions about your class in general in 1510, feel free to reach out to me. And good luck with the quiz today. Bye, everyone. I'll see you next time.
Thank you, Professor. Have a good
Bye.
weekend.
Have a
Thank you.
good
Bye-bye.
Bye-bye.